Okay, so yeah, so we'll be covering mainly group actions and other things related to it, right? So Cayley's theorem. So what Cayley's theorem says is very simple. If every group G is isomorphic to a subgroup of the symmetric group SG. So symmetric group SG is essentially the symmetric group which is kind of induced from this group G, right? So symmetric group generated by the elements of group G, you can say. So every group G is going to be isomorphic to a subgroup of the symmetric group generated from that group. Okay, and if your if the order of your group is equal to n, then G is going to be isomorphic to a subgroup of Sn. So that's the symmetric group of n items and elements, whatever. Okay, so the proof for that, this is quite detailed. If you look at R10, R10 just says it in one line, I believe. Now, since the operation of by-left multiplication is faithful, and G is isomorphic to its image in the permutation of G. So permutation of G is the notation that's different from S sub G in Rothman. Right, so that's just permutation of all the elements of the group G. So yeah, he just finishes it in one line. But if you look at it in detail, in Rothman, supposed to be the collection of bijections G to G. Yeah, right. I mean, symmetric group is essentially that. So you're just going to have permutations of all the elements of the group. Right. So permutations can be transpositions and or cycles. So yeah. Okay. So so this is how he does. He takes an element from the group and defines this translation as a map. So this is tau of the element going from G to G. What it does is takes an element X and gives you AX, right? So that's the translation map. And here X is again an element of G. And if like, I mean, this is not necessarily a homomorphism, but it's only a homomorphism when A is equal to 1, right? Okay. So what you do is you use this definition of the translation, and you do that for two elements A and B. So you have tau of A and tau of B. You take the composition of those two translations, and then you apply it on some element X of G. So that will be tau of A, acting on tau of B of X. Right, so that will be tau of B of X is just Bx. So that will be tau of A of Bx, and this is just A parenthesis Bx. So you have the this is the multiplication under the group G. But as it's a group, so it's associative, so you can have ABX. Okay, so what this says is that tau A times tau B is equal to tau of AB. So if you multiply two translations, that's equivalent to taking the translations of the product of which you're taking the translations, right? And this says that this is a bijection. Each translation is a bijection, because if you look at this inverse, tau, so the inverse is going to be the translation on the inverse element in the group, right? So you had A, the inverse element is of course A inverse, so you're going to apply tau on that, and when you take the product, tau A times tau A inverse, you're going to get, of course, by what we established here, you're going to have tau of A times A inverse, and that's just the identity. So it will be tau 1, which is just the identity of the group, right? And that's equal to the other way around, because we had the associativity working, right? So what this means is that each of the translations is a bijection, and of course, as Baltus pointed out previously, this is an element of SG, and SG is the collection of such taus which are bijections. Okay, I hope that's clear. So now what you do is you define again a map phi going from G to SG. What it does, it takes every element from the group and it gives you a translation of that element in SG, because SG is filled with these taus, these translations. So what you do is you again apply the fact that you just take two elements from G and then you multiply. So phi of A times phi of B is going to be equal to tau sub A times tau sub B. But as we know, again, tau sub A times tau sub B is just tau AB. That's equal to phi of AB. So this smoothly works out to phi being homomorphism, right? So so phi is a homomorphism. Now we have to show that it's injective. So if it's injective, let's see. We have to check if for any two elements A and B, phi of A is equal to phi of B, then a tau of A has to be equal to tau of B. So the translation of those two elements have to be equal, right? So so yeah. Okay, yeah, so I just got lost, but phi of A is equal to, if phi of A is equal to phi of B, then you're going to have tau of A is equal to tau of B, and that means whatever x you're taking from the group and acting the translation upon that, you're going to have the same thing, right? But so the translations are equal if the this homomorphism for the two elements that you're taking translation of is equal, right? So and this translation gives exactly the two elements A and B when x is equal to 1, because then your translation is just going to give you the same element back, right? And so this this showed us that there is an isomorphism between every group G to the symmetric group SG, right? So for the second half of the proof, which is to show that if your order of the group is N, then it will be isomorphic to Sn. But he kind of cites this exercise, from which he uses a result. But you can pretty much see that if your group has order n, which means it has n elements, then you're going to have this isomorphism is going to give you translations of each of the n elements, right? So the set that you're going to form with this isomorphism is going to be exactly the permutation of n elements, and the permutation of n elements, as we know, is Sn. Yeah, hello, chair. Yeah. Okay, so this was Cayley's theorem, and it's not entirely interesting, which both Rotman and Artin agree upon. Rotman directly says that it's only mildly interesting, but yeah. So this is the Cayley's theorem, and if you can remember, we had Cayley table, right? Cayley's table where you draw the table for all the multiplications that you do in a group, and using the law of composition, and this is exactly that. This is just this permutation TA is going to be the 8th row. So the rows would be the permutation. So let's go back and take a look at the Cayley table. I guess we saw that in autumn. Yep. So this was what we saw, and we had several maps, right, transposition and stuff. But each of them is essentially um, a translation. And so tau A in Rotman is the eighth row. So that's like the you're using the translation on the eighth element, right? So yeah, that's that. Okay. So we have a few interesting propositions and theorems are resulting from this. We will not be able to go through each of them and prove each of them, but we'll at least state them and prove some of the interesting ones, but others you recommended to go through um, on your own. And the examples. Rotman is filled with examples, which are kind of important because it introduces some interesting concepts to the examples. So yeah. Let's see. So this theorem says that you have a group and you have a subgroup of G, which has a finite index n, right? So if you remember index from our last time when we discussed group theory, the index is just the number n such that um, any element to the power of that gives you the identity back, right? So that's it has a finite index n. Then there exists a homomorphism from the group to the symmetric group of n elements with the kernel of the homomorphism being less than or equal to h, in the sense that it will be a subset of h, right? A subset of the subgroup. So this is something that you might remember. Wait. Okay, yeah. I think I messed up with the definition of order and index. Yeah. Let me recheck. Uh, yep. The number of left cosets of a subgroup is called the index of H. Yep. Yep. Thank you for mentioning that. Otherwise, I would have continued with that wrong definition in my mind. Yeah. So index is your number of left cosets of a subgroup, and it's denoted by this. We saw that last time. Like this, within close brackets of G is to H. So that's the index of H in G. Okay, so we're going to try and establish a homomorphism between this group and the symmetric group such that the subgroup of that group G contains the kernel. Okay, so G mod H denotes the set of all cosets of H, right? So you remember that's the notation we also used in R10 for quotient groups, except we don't have a normal subgroup here, so we can't have a quotient group, but this is the set of all cosets. So for each element, now you again define a translation map, right? So the translation map here, tau A, takes you from the G mod H to G mod H by taking every coset and essentially, translating it by the element A. So T tau A of XH gives you AXH, right? So that's another coset in G mod H. You do the same trick. You take two elements in G, tau A circ tau b, and you apply that to a coset xh, so we'll have tau a of tau b of xh, and at the end you're going to have a times bxh, which is equal to ab times xh, because we have associativity. So again, tau a times tau b works out to tau ab, right? And thus this is also a bijection, because if you check the inverse like we did last time, it's essentially the same thing, that you're going to have the identity in the set of all cosets, the G mod H set. Okay, so this S of G mod H, like SG, is filled with these bijections tau of A, which work out like this. Now what you do is, you, like before, you define a map taking you from G to S of G mod H, which gives you a translation for each of the for so you have, like, you take an element from this map phi, it gives you a translation, and this is a translation of cosets, right? So again, you do the same trick, you apply this to two elements, you get that phi of AB is equal to phi of A times phi of B, right? So this is a homomorphism again. So what this means is that you know, for every group G, if you have a subgroup of G having finite index, you can have a homomorphism between G to Sn, right? Yeah, and I believe okay, so we'll see this again, but yeah, if your element A is in the kernel of the homomorphism, then every element A is going to be mapped to the identity in the G mod H set. Sorry, yeah, G mod H, so that tau A of xh is going to be equal to xh, right? So it's going to give you the same coset. Give me a second so that I can enable my do not disturb mode. Okay. So yeah, so essentially when you have elements on the kernel, they're going to map to the same cosets, right? And if you have x as 1, then you're just going to get the subgroup back, right? Okay, and similarly, if your order of the G mod H is n, then S of G mod H is going to be isomorphic to Sn, because again it's going to be a permutation of n elements. It will be a permutation of n cosets in G mod H. Okay, so that went well. He has a few propositions and a few examples. Okay. By the way, do you hear any kind of noise from my side? I don't think you should, but if you do, let me know. Okay. So this proposition, which I'm not sure if we can go through, but we'll try. But I believe it'll be a nice exercise of dihedral groups and stuff. Let's see. So this proposition says that every group of order 4 is either isomorphic to I4. So here I4 is just Z mod 4Z. right? So it's the integers modulo 4, that is all the integers that are multiples of 4. Um, so it's either isomorphic to that or the kind 4 group that we saw before, which we didn't go much deeper into, but yeah. But yeah, moreover, your I4 is now going to be isomorphic to the kind 4 group. Okay, so if you remember Lagrange theorem, we know that Lagrange theorem says that if you have a subgroup of a finite group G, then the order of the subgroup divides the order of the group, right? That's basically the Lagrange theorem. Um, but yeah, so if you have like a group of order 4 by Lagrange theorem, every element in G other than 1 has either order 2 or 4, right? So this is kind of, if you go back to the P set on group theory, you'll see that there's a problem related to something like that. Not exactly, but yeah. So by Lagrange theorem, what it means is that you're going to have every element in G other than the identity will have the order 2 or 4 is not going to be able to have something 3, because 3 does not divide the order of the group G itself, which is 4. So you're going to have 2 or 4 itself. So if it's an element of order 4, then of course G is going to be a cyclic subgroup. I mean, it's going to be a cyclic group, right? Because every element of that has every element of, right? Yeah. Okay. Your order is 4, which is equal to the order of the group, so you'll have the cyclic group. Otherwise, you're going to have the order as 2, so that'll be x squared is equal to 1, which means that, you know, the elements themselves are the identity, so the inverses of themselves, and that means you're going to have an abelian group, which is something that we've done exactly before. Okay, so if you're going to have two distinct elements, x and y, which are like non-trivial, so they're not the identity, then you'll see that G is going to have 1 x, y, and x, y. Okay. I'm kind of skeptical at this point, but is it clear why G is this set? I guess it is. Okay, so if you try to have this bijection F from G to the Klein V group, which fixes the identity, then f of x is the multiplication of two transpositions. So you have 1, 2, 3, 4. F of y is 1, 3, 2, 4, and f of xy is 1, 4, 2, 2. So this is similar to, if you go back to R10, let me see the page number. If you go back to R10's, R10 has something similar. Right, page 51. He does exactly the same thing, but this is not about the Klein V2, but bijection gives you exactly the elements of the kernel that's in page 51. Let me show you in Norton. Give me a minute. Okay. It looks like that due to the closure of I'm not sure. Can you explain why it's because of the closure? Yeah, so this is the what I was comparing with. You have the same transpositions, multiplication of transpositions. And elements are by assumption of order 2. Yep. And elements are by assumption order 2, so you have 1 xy. The fourth element cannot be xx or yy, so it must be xy. Okay. Makes sense. Okay. This proposition is kind of more interesting, so we'll see that. We'll try not to spend too much amount of time here because of that other more interesting stuff, but let's see. Okay, so you have the proposition 2.90, which says that you have a group of order 6, then G is going to be either isomorphic to I6 or S3. So this is similar to what we saw before, right? So we saw that the group of order 4 is either isomorphic to I4 or the Klein V group. But here you have I6 or S3, right? And you'll have to also establish that I6 and S3 are not isomorphic, right? Okay, so this is kind of also similar to what we've done before, but let's see. Again, by Lagrange Theorem, the only possible orders of non-identity elements are 2, 3, and 6, of course. Otherwise, you're not going to be divisible with the order of the group. So G is isomorphic to I6 if G has an element of order 6. That's trivial. This exercise on page 62 shows that G must contain an element of order 2, so T. Let's see. I'm not sure which exercise he's talking about, but I guess that we have an intuition about what that is. You have an group of order 6. So you might have an element of order 2. To prove that it must have an element of order 2, you'll have to do something similar as you did with the group of order 4, right? But essentially, if you have a group of if you have an element of order 2, Okay, so let's see what exercise he's citing here. Page 62. Is that 2.23, right? If you have an element, okay. This element y has order m. If m is equal to okay, so m can be written as the product of some prime p and some element t. Prove that yt has order p. Okay, so this is yeah, this is kind of something we've done, isn't it? I guess it was something in the p set. I'll have to look which p set, but we had something with powers of prime. Okay, so 2.27 it was. Oh, okay. Sorry. Yeah, it's just 2.27. Okay, thanks. Um, 2.27 says that if you have a group with an even number of elements, prove that the number of elements in G of order 2 is odd. Oh, I think this is exactly the p set problem we had, isn't it? Let me look at the p sets. P set 3, I believe. Then maybe p set 4. P set 4 was on rings. Okay, so we put this exact problem in the p set. Okay, yeah. And I forgot about it somehow. But yeah, so we had this problem in the p set, and so we can use this result pretty much directly. So yeah. So that's the reason why it must contain an element of order 2, right? Okay, so that makes sense. So you know, so if it has order 2, all the elements are going to form an abelian group, right? So G must either be abelian or it will not be abelian. So you consider just the cases of when the order is 2 and when the order is 3 of the elements. So case 1, if G is abelian, if there is a second element of order 2, say A, then it is easy to see that it's going to be commutative. So AT is equal to TA, that you can have a subgroup which contains 1, the identity, the element A, T, and AT, right? Because it's going to be a subgroup because everything in H commutes. But this contradicts Lagrange Theorem because this has the wait. right? The thing is, this subgroup has order 4, um, whereas the order of G is 6. So, of course, it's not divisible, so um, it's not possible. It follows that G must contain an element B of order 3. But so essentially, you're going to have some element which has order 2, but every element cannot. You cannot have a subgroup, because if you have a second element of order 2, then you're going to get the subgroup for each of these elements, and that's contradiction. So if your second element is not of order 2, then it must be of order 3. So if it is for order 3, then TB is going to be of order 6. So TB is of order 6, proposition 2.82. Do you want to see that? But I believe it's because right, so if we have two commuting elements of orders m and n, then their product is going to have the order mn. Okay, that makes sense. The proof is pretty much straightforward, because you take the power of the product, because they commute. You can take it either way, and then compare it with the identity. Okay. So let's get done with this. So if SG is abelian, um, if and only if it is if all the elements of hmm wait right. So G is abelian if and only if the elements you're going to have elements of order 6, right, which is the order of the group, thus making it cyclic. Um, that's the case when G is abelian, implying the group being cyclic. So the case 2, when you have group G is not abelian, you're going to we're going to have to look at different cases. But okay, so if G has no elements of order 3, then you're going to have x squared equals to 1 for all the elements of the group, and it's going to be abelian, which is what we know already. So then that's not possible. So it must contain some element of order 3 as well as an element of order 2, right? So this is the notation for the cyclic group generated by S. Remember, so the order of the cyclic group generated by S is 3. Okay? Now the index of the cyclic group with respect to the parent group G is equal to um, you know dividing the order of G with the order of the cyclic group, right? So this is of course something we know as the counting formula. Remember, uh, the order of the group is equal to the order of H times the number of processes, which is just the index of the subgroup, right? So here the subgroup is just the cyclic subgroup. So here you're going to have the index of the cyclic subgroup is going to be 6/3. That's 2, right? So what that means is that it's a normal subgroup of G by proposition 2.62. Proposition 2.62, what that is again. Oh, of course, yeah. So I thought it would be something else, but if you have an index 2 subgroup, then it's going to be normal. That makes sense. Okay, so that's that. Now, if it's a normal subgroup, as T has order 2, so the inverse of T is just going to be the element T itself. So T is equal to T inverse. But as the cyclic group generated is a normal subgroup, so all the conjugates of with respect to T are going to be in the normal subgroup. Right? So TST is in the cyclic subgroup. So like TST, then as it is in the cyclic subgroup, so it must be generated by the element S by some power of it, right? And this power can be either 0 or 1 or 2, right? Because that's what you're allowed to do in the cyclic subgroup, I guess. Yeah. So if I is not equal to 0, because if you have I is equal to 0, then you're just going to get the identity. But if I is equal to 1, then TST is equal to S, which would mean S and T commute. And this means that if S and T commute, then ST as a product is going to have order 6, right? So that goes back to case 1, which we saw. It will be cyclic. Therefore, the I must be 2. So TST is equal to S squared. That means TST is equal to S inverse. Alright. Okay, so now as before, what you do is you try to construct an isomorphism which takes you from the group G to S3, and here the subgroup H that we considered before is just a cyclic group generated by T, right? So as before, you have this homomorphism taking you from the group to the symmetric group of G mod T, mod the cyclic group of T, right? So that's all the permutations. What it does, again, simply wait, phi of G takes X times, oh, of course, right, it's going to, it's kind of confusing, wait. Yeah, right, so this is something like the translation map that we saw before. So, you're going to have an isomorphism between G and S3 because of the theorem that we proved of the representation in cosets, this thing. And your kernel of the homomorphism is going to be included in the subgroup itself, right? So the kernel of phi is included in the cyclic group generated by T, which means that the kernel is going to be the identity. That is when the phi is going to be injective. Because if you think about it, if phi is injective, the only things that you're left with is 1 itself, like the identity. There's nothing else that you will be able to have as the kernel, right? Because nothing else maps to the identity. But the other case is when the kernel is going to be the subgroup, the cyclic subgroup itself. So, yeah. Okay, so if that's the case, then G mod T, which is going to contain all the cosets, will be the cyclic subgroup itself. It's going to contain S times T, the cyclic subgroup, then S squared times T. Okay. and we can write that in as a matrix like this. Okay. So that's when but like, yeah, if the other case is like when your phi of t is going to be the identity permutation, right? What that means is that, you know, when you multiply t as with t as with like the coset, it's just going to give you the coset itself. So it's exactly analogous to what we saw here. You know? If it's an element of the kernel, that is, it's going to give you the coset itself. Okay, so therefore t cannot be in the kernel, and this isomorphism uh, right, so this isomorphism that you have to this symmetric group, the symmetric group happens to be isomorphic to S3, just as we saw here, the symmetric group of G mod H for any subgroup is isomorphic to Sn when n is the order of the G mod H. Right? So here the order is just 3. So yeah, and this phi happens to be injective, just like before. It's going to be injective homomorphism, um, but as it is injective, and since like both the like G has order 6 by definition, and S3 has order 6 as well. Thus, it has to be a bijection because it is injective and all the you have the same number of elements. I mean, you have the same order, right? So G, the group itself, is isomorphic to S3. Right? Um, so that's what we had to prove, and yeah, and proving that like I6 itself is not isomorphic to S3 because that's simple enough. I6 is abelian, right? As we used in this case. Um, so, but S3 is not abelian in any manner. So, okay, yeah, but yeah, hello JP.
Hey there, looks like I came in at a good time, just in time for group actions.
Yeah, exactly. We are done with all the Cayley stuff. Okay, so let's see what we mean by group actions. And it gives a number of examples of that, and we'll see. Okay, so you have a set X, and you have a group G. Now this group is going to act on the set if you're going to have a function taking you from the Cartesian product of G times X to X, right? What it does is takes an order pair of an element from the group and an element of the set, and it maps to a product G X, right? Such that this product is associative, so GH times X is equal to G times HX, and 2, it has an identity. Okay? So 1 times X is equal to X. That is one of the identity for all the elements of the group. Right? So this, you might think, is kind of like um, an extension of applying the group structure onto another set, right? Because the set X is just a naive set; it has nothing but elements. But this group is going to act and influence its properties of whatever it has, the group structure onto X by taking this nice function which takes an order pair. So you have two elements from the group and the set, and these conditions ensure that you have a group-like structure on X. Okay. So that's that. So this is going to be, so X is now going to be a G set, right? Because your set is acted upon by the group G. Okay. So let's see. Yeah, so this is kind of important too. So if your group acts on a set X, like let's say you have this element, like first variable, yeah, element G. So you have this function alpha G taking you from X to X. What it does, it takes an element X and it maps to G times X, right? So you can think of like this alpha, these alphas like take take each G and give you Gx. Now if you do that for all the elements in the group, you're going to have all these alphas, and that will make up what we have as the function here, right? Giving us all the Gx. So yeah, so then he says this function is a permutation of X, because if you look at its inverse, that's going to exactly look like what we saw in the translation. Right? So alpha G times alpha G prime, so the G inverse is going to be alpha of 1, which is just the identity. Right? So so alpha, right? So this alpha defined by taking taking group elements and giving you these permutations alpha G's, is going to be a homomorphism, right? So these permutations together make up the set S X, right? So Sx is just the permutation of the elements of X. So that's a symmetric group. And you have a homomorphism which lets you have this. Okay. Yeah, so the main idea is that this action of a group is essentially another way of viewing a homomorphism, which gives you these permutations from a group. Okay. We're going to see a few examples related to conjugation. Let me just check if none of these examples are trivial and which are important. Yeah, he mentions a lot of lemmas. We'll not be able to go through each of them and prove them, but let's see. So this example is, the function that you define is just the conjugation. So for every element you get the conjugation. So alpha g of x is equal to gx times g inverse. So this is the conjugation. The function gives you the conjugations, right? So we have to first of all ensure that you have associativity, right? So you take two elements and their conjugates. So alpha g circ alpha h, and then you apply it on some element at g of g. So this is just again alpha g times alpha g of alpha h of x. Alpha h of x is just hx h inverse, the conjugate. Then you'll have the conjugate of this whole thing. But as these are all elements of the group, so G, H, X are all the elements of the group, so you can have associativity there, so you can like play with the brackets there, arrange them in this manner. So then now they become the conjugate of X with respect to GH, right? GH as an element of G. So alpha G circ alpha H is equal to alpha GH. just as it were the translation. So this is very nice. I mean the way he introduces this makes more sense, because once you grasp the idea of translation, which he introduced early enough, then all of this is kind of like an extension of that. So this seems a very nice way of doing that. So yeah. Now for Axiom 2, you have to ensure that you have an identity. So for each x, alpha 1 of x, where alpha 1 is the identity of the group, alpha 1 of x is just going to use again the conjugate 1x times 1 inverse, and that is x itself, right? So we're going to have that alpha 1 is the identity of the group itself. So this gives us how the conjugation works with the group actions. So we have following two definitions and then a few examples relating to the definitions. Let's see. The definition is that of an orbit. So if G acts on a set X, and you have an element X from the set, then the orbit of the element is going to be this subset of X, which is defined like this. So this is O of X is all the elements Gx such that G is in G. Right? So this is like all the kind of like multiples of X, something like that. I mean all the products that you can do with X, right? So Gx, that's that. And this is going to be a subset of X itself. Then this is the orbit. I'm not sure why you're using the terminology of orbit, but yeah. Then the stabilizer of the element X is denoted by G sub X. Then this is a subgroup where this is all the elements from G such that when you multiply that with the X, you're going to get X back. So Gx is equal to X. And for all those G's, you have a set which you call not really a set, it's a subgroup. It's a subgroup of G. Okay. Okay, so yeah. We have a few examples relating to this, but I think he says something else. If G acts on a set X, then you define a relation, kind of like establishing an equivalence relation. So X is equivalent to Y, such that you have a Y that is equal to Gx. Okay. Then you're going to have an equivalence relation with equivalence class. Classes would be the orbits. Okay. Okay. So Cayley's theorem, as we saw, said that you're going to have translations, and you're going to have permutations. So these translations that you have, like tau of G, which like take an element and then give you the product Ga, then the orbit of A is going to be the group itself, right, for these translations. Because if B is again an element of G, then B can be written as BA inverse times A, and BA inverse can be written as, this whole thing can be written as tau BA inverse times A, because that's how you define the translation, right? So the stabilizer of the stabilizer G sub A, so the stabilizer of A is going to be all the elements that are mapped to GA, right? And there are none. Thus, you are left with only the identity, right? And this is precisely because if there is an element A, if there's an element G such that you can like map it onto GA, and that's because that's what you need here. Then G has to be the identity. There's no other ways. Because of the way we have defined um, the um, the translation here. Okay, so yeah, there's only one orbit. Then if you look at G acting on the family of cosets of a subgroup, H, by translations. So what you're going to do is you're going to take a coset AH and you're going to map it onto GAH, right? And so if you look at the orbit of this coset, you're going to be left with the whole family of cosets, right? Because again, just like here, if you have a BH, a coset, then it can be written as written as in the sense you can map some coset to BH by this translation, tau BA inverse, right? Because tau BA inverse is going to give you like BA inverse times AH, and BA inverse times AH is just BH. So you're back at the coset. So G acts transitively on G mod H. That is to say, there is just one coset. So there's just one orbit, right? And the stabilizer for this coset AH is going to be the conjugate of the coset. So AH A inverse, right? Because if you have anything else, like GAH has to be equal to AH, then this is only possible if like when you multiply A inverse on both sides, A inverse GA has to be in H, right? And that happens if and only if G is in here. So this is the stabilizer for the coset AH. Okay. He considers a few other things, centralizer and normalizer, which are also important. Um, Then we have the class. Okay. The class creation. Yeah, so we'll not be able to go through all of this, but let's see. So that's how it works for conjugation. So with this, you can have a conjugacy class, just like before. We were talking about establishing an equivalence relation. So let's see. When a group G acts on itself by conjugation, then the orbit is going to be all the elements of G such that Y can be written as some conjugate of X, right? So in this case, the orbit of X is the conjugacy class of X, right? And it's denoted as X G for some reason. Indeed, and if as we've looked at some previous theorem, if you take an element from Sn, then the conjugacy class of alpha is going to consist of all the permutations in Sn, and it's going to consider all the permutations in Sn that have the same cycle structure as alpha. So like if alpha is in Sn, it has to be like a 4 cycle or 5 cycle or 3 cycle, something like that. So the conjugacy class of alpha is going to be all the permutations in Sn that match that cycle structure. So yeah, so that's the conjugacy class. Then how? Okay, so they relate this to the centralizer. So centralizer is of course something that we've seen. This is all the elements of the group that commute with all of the elements. So an element Z lies in the center of the group if and only if the conjugacy class of that element is equal to the singleton Z. Right? So there are no other elements in G that conjugate to Z. And yeah, that makes sense. So then if you have some element again, so this is again the opposite direction. Take an element from the group. The stabilizer of X is going to be CG of X, like CG, okay, of X, such that this is all the elements with X can be written as the conjugate of X, GX, G inverse. And so this is a subgroup of G, obviously, and these are all the elements that commute with X, and this is the centralizer of the specific element X in the group, right? So yeah, interesting stuff. Yeah, so this is about the normalizer again. The same thing, you have a set X, then you have a group G that acts on the set X. Now you have the action is just taking every subgroup and writing it as AHA inverse, okay, where H is a subgroup of G. Okay, so if H is a subgroup G, then a conjugate of the subgroup, it's a subgroup of G itself, but it has this specific form. This is just all the elements which are conjugates of all the elements of H, right? So yeah, and and this conjugation, this mapping is an injection, right? And this image is that entire set itself. So yeah, and this is okay. So conjugate subgroups then are going to be isomorphic to each other. That makes sense. So for example, in S3, all cyclic subgroups of order 2 are conjugate because I think this is something that we saw before. But yeah, and this makes more sense because if you have a subgroup H that consists of all the conjugates, then the orbit of this subgroup that consists of all these conjugates. Right, okay. Yeah. Yeah, so the orbit of a subgroup H is going to consist of all its conjugates because that's how you define an orbit. um, hmm, you know, then H is going to be the only element in the orbit, if and only if H is the normal subgroup of G, right? So that is, the conjugate of H is H itself, right? And the stabilizer of H is going to be just like the case here. Instead of taking a single element X, you take the whole subgroup H. So Ng of H is equal to all the elements in G, such that the conjugate with respect to G of H gives you H back, and that's the normalizer. Right? So centralizer, normalizer, hopefully making sense. Okay, now give me a minute, I'll be right back. Okay, bouncer stack, cool. Um, yeah. So yeah, we are done with normalizer. Let's see what else we have. Dihedral group. I'm not sure if we need that. But this proposition and the theorem seems important, so let's go through that. And there's this Koshi Theorem. Okay, so this proposition says that if G acts on a set X, then X is the disjoint union of the orbits. Right? So if you have an action of a group on a set, then the set itself can be presented as the union of the orbits of the set, of each of the elements of the set. Right? So this is what it is. The proof is, as I mentioned earlier, the relation on X given by X is equivalent to Y, and there exists G such that Y can be written as G times X. With an equivalence relation with equivalence classes. Okay, so this makes sense. So you have this equivalence relation, and the partitions which arise from this equivalence relation are going to be disjoint sets, right? And these disjoint sets are the orbits themselves, and so the orbits partition X, and you see that with this equivalence relation, and so if you take the union of all these partitions, you're going to get X itself. So it's because it's the partition, right? That makes more sense. But if you have X is finite, so the order of X is equal to the summation of um, all the orbits, order of all the orbits, right? And okay, so it doesn't give anything else, but the count is going to be same because in the order you're going to only have unique elements such that this holds, and they are all disjoint. So when you add them all up, they should amount to essentially all the elements of X. I mean, the thing is, with this order, you're not really doing something with X. You're just like, you're not introducing any new elements. You're just partitioning it. And so when you like take the union of all these partitions, and even if you just take um, the cardinalities of all the disjoint subsets, then they will add up to the cardinality of the set itself. So yeah, so which is like this proposition. The corollary of this can be this theorem, which says that if G acts on a set X, then you have an element X from the set, then the order of the orbit of that element is equal to the index of the stabilizer. Right? Because stabilizer we know it's a subgroup of G. So that makes sense, but let's see the proof. The proof sounds simple enough. So just like before, we have G mod G sub X. So G mod the stabilizer is the family of all the left cosets of the stabilizer. Right? So that's G mod the stabilizer. Then you try to have this bijection phi going from G mod stabilizer to the orbit, right? So what it does is it takes each left coset from the G mod stabilizer, and it maps it onto maps it to get something in the orbit, right? Something you can write as the product. And if you can have this as a bijection, so right, so this is a claim that if you're able to prove that this is a bijection and it's well defined, then it is trivial to say that the order of this domain G mod stabilizer is going to be equal to this, because again, if you apply the counting formula on this, and then it's just going to be what was that? No, not sure how to call it. But yeah, we just saw that, right? If you apply the counting formula, you're going to get something like this. Okay. So yeah, so now we check if this is well defined. So what you do is you define phi to take the cosets of the stabilizer, left cosets to Gx, that is in the orbit. Now this is well defined because G of the coset is equal to like if you have like two cosets are the same, like G times the stabilizer is equal to H times the stabilizer, then okay, so then H can be written as G times something from the stabilizer, G sub X, right? Okay, for some F that is specific because f of x is equal to x. Okay, so if f of x is equal to x, then g so h would just be hx is just going to be gx, right? So all the cosets that you get from h and g are going to be the same. Okay, so this is a well-defined function, right? Now to prove that this is a bijection, you have to prove the injectivity. Okay, so if you have two things like g of x is equal to phi of this coset generated by g, that is equal to coset generated by h, because uh, hx is equal to gx, because there is always some f which will let you have that. Um, okay, so yeah, so that works. Then h inverse times gx, then is just going to be um, you know, x itself. You can write that. Okay. Yeah. So then h inverse times g is going to be in the stabilizer, because of course it can be written as, when you like take the product of x, it gives you that x. So it's in the stabilizer. Then um, the cosets are equal. Okay, so that proves injection, right? If you take gx is equal to hx, you get the cosets are equal. So that implies injectivity. Now for subjectivity, you take an element in the order, sorry, in the orbit, then it can be written as some g times x, right? Um, and as we know, gx can be written as just the image of the coset generated by g, right here. So y is equal to phi times this. That means, there's always something that you can map to y. Okay, so then he gives some example about the dihedral groups, which talked before, but we're not going to get into that. Okay, so we have a few corollaries. Let's see. Then we have the Cauchy theorem. Cauchy theorem. Okay. So the first corollary is that if you have a finite group acting in a set, then the number of elements in any orbit is going to be divisor of the order of the group. That makes sense, because every orbit is going to be a subgroup. Every orbit is going to be, um, I mean, it follows directly from here. Um, the orbit of x, I mean, the number of elements in any orbit is essentially the order of the orbit. Except the thing is, yeah, orbit is just a set, so the number of elements is going to be equal to the index of the stabilizer, and the index of the stabilizer has to be a divisor of g, order of g, because the stabilizer is a subgroup of g, right? And that follows from Lagrange Theorem. Okay, so the next corollary is that if x lies in the group G, then the number of conjugates of x is the index of this centralizer, right? So if you take a look at the index, the order of the number of conjugates of x, so that is x to the G, which is like the the conjugacy class, remember? So xg, um, taking the number of elements in there is going to be equal to the index of the centralizer, because the centralizer contains all these elements, right? Okay. And the next one is essentially just another application. If you have a subgroup instead of just an element, the number of conjugates of the subgroup is um, going to be the index of the normalizer. Right. Okay. So we come to the Koshi Theorem. So the Koshi Theorem says that if you have a finite group whose order is divisible by a prime, then G must contain an element of the prime order of G, right? So yeah, let's look at the proof. I'm probably going to use something that we just saw. But let's see. The Cauchy theorem is simple enough, but so they prove it by induction. Okay, so so induction starts from n greater than or equal to 1. So G, the order of G is equal to P times M. Okay. So if M is equal to 1, this is true, but we'll have to prove the inductive state. Okay, so you take an element from the group, you count the number of conjugates it has, and just as we saw, the number of conjugates it has is equal to the index of the centralizer. Now, if X is not in the center of the group, then the number of conjugates is going to have more than one element, because if your X is in the center, you already know that it commutes with every other element. So the number of conjugates is just going to be the identity. There's nothing else. So X to the G, that is the number of conjugates, is has more than one element. So the number of elements in the centralizer of X is going to be less than the order of G. That makes sense. Now, if P divides the number of elements in the centralizer, right, for some non-central X, so X is not in the center of the group, then by inductive hypothesis, you're going to have an element of order P in the centralizer of X. Alright? Makes sense. If P divides the number of elements, then there is an element of order P in the centralizer, making the centralizer a subgroup of G, right? And thus then it's done directly by Lagrange Theorem. If you assume that it's not divisible, so P does not divide the number of elements of the centralizer, yeah. As P is a prime, then mod of G, the order of G is going to be equal to so this is just by the counting formula, right? The order of G is equal to the index of the centralizer times the number of elements, the number of elements in the centralizer of X. So this is confusing because of the notation, but yeah, so this is directly from the counting formula that we know. Okay, so as P does not divide this thing, right? So P cannot divide the number of elements you have in the centralizer of X, but P does divide the order of G, and because that's P itself. So P must divide this thing, and that's basic thing. That's also one of the things that we saw in ring theory, but that's just you know, trivial enough as division. So so P divides the index of the centralizer of X. Now so the center of the group consists of all the elements such that right, so if right, so the center of the group consists of all the elements such that their conjugacy class is essentially the identity, because once you have elements in the center, the conjugacy class is essentially non-existent. So we use the formula that we saw just in the above theorem about the summation of orders. So the summation of orbits is equal to the set on which you're having the action. We use that to denote that the order of G is equal to the order of the center of G plus you add all the indexes, right, of the centralizer of all the elements. Okay. This is not confusing, but it's straightforward. Just that you take the centralizer of all these elements xi, and xi are supposed to not be in the center of the group, right? Otherwise, there's no point. So you take the centralizer of all these elements, then you index them. So you have an index of all these centralizers with respect to the group. Then you add all these for all the xi's, and when you add that with the center order of the center of the group, then you're going to get P. Right? We know that all these are divisible by P, right? From here, and this is P itself, right? This thing must also then be divisible by P, but the center is abelian by definition, right? And if it is abelian, it has to be if wait. Right, so this by definition, sorry, by a proposition that we did before 2.78. Yeah, if you have a finite abelian group and you have a divisor of the order of that group, then G must contain a subgroup of order. We just need that we have an element of order that divides the prime, right? So what was that? This. So the center, sorry, the order of the center is divisible by P, as that is abelian. We can say that the group must contain an element of order P, and then we're done with the proof. Koshi Theorem. Okay, so that was Koshi's theorem. Now we go on to the next important thing, that is the class equation. So the class equation is essentially just what we saw. For every finite group, you can have this classification, which is that you can write the order of the group as the order of the center plus a summation of all the centralizers. Right? Now, if P is a prime, then a finite group G is going to be a P group. So P groups over here, P groups are going to be important. Let's see. So if P is a prime, then for a finite group G, the pre-group is going to be when your order of the group is equal to p to the n, p to the some positive integer, right? This is a finite p group. It talks about the fact that there are some infinite p groups, which he describes on some other exercise. Okay, so this is a p group now. If P is a prime and the group is a P group, then the center of the group is cannot be trivial, right? Yeah. And that makes sense, because each of the centralizers is a proper subgroup. So your indexes are going to be you know not one. But as P is G is a P group, then as G is a P group, right? So you have the order of G is just P to the n. So as we know, P divides all these indexes, so P must divide the order of G as well. Right? It would not because previously the order of G was just P. Here the order of G is P to the n. So if it's P to the n and this is a multiple of P, then it's going to divide this. So then as it divides, then it itself is going to be a power of P for sure. So if that's the case, then P divides each of the terms in the class equation. It divides the center, it divides all the indexes, right? So it must divide the center, and if it divides the center, it cannot be the trivial subgroup. Okay, so that was that. We have a few corollaries, some interesting examples. We talk about Fermat's little theorem, I believe. Yeah, which is pretty interesting. So we'll try and go through this, even though we'll not see this again, I believe. But then he has some other interesting propositions. And this is pretty long. I believe there's some use of combinatorics, which I'm pretty bad at. I see some coloring and stuff. So, yeah. Second proof of Koshi Theorem. I mean, this was kind of satisfactory. I mean, it made sense. So, yeah. Is it? Ah, 2.105. Ah, so this Fermat's theorem is essentially that proof. Ah, okay, and I was interested in that, but okay. Let's see. Hmm. Okay, leisure reading. That would be nice. Okay, so we can skip this and talk about other things. One of the corollaries of Koshi Theorem is if P is a prime, then every group of group G of order P square is going to be abelian. That makes sense. I mean, If G is not abelian, then the center is going to be, of course, it's a proper subgroup. So its order is going to be 1 or the prime P sub, because there's nothing else that's going to divide. Um, there's nothing else that would divide P squared. But we know that the center is not trivial, so the center must contain P elements. So the center is always a normal subgroup because there's always abelian. So quotient G mod the center is also defined, right? And it has order P. Hence a G mod. Okay, so it has order P. So that means the quotient group is going to be cyclic. Yeah. I see. So proposition 106. Let's see. If G is a group of order P to the E, then G has a normal subgroup of order P to the K for all the K's less than E. And this is, I believe, this is straightforward enough. You just need to apply induction for all the elements that are less than E. I believe there's nothing else to it, but let's prove the last to the proof. The base state is also obviously true, because if E is 0, then this is the trivial. It's trivial. Wait. Okay. The center of G is if it's a non-trivial normal subgroup, right? Then you consider a subgroup of the center which has order P, right? So it's any subgroup of the center. Then the subgroup Z is going to be a normal subgroup of G. Okay. Now, if you have all the k's that are less than or equal to E, then P to the K minus 1 is less than or equal to P to the E minus 1 for sure. And P to the E minus 1, wait. Is equal to the order of the quotient with G mod H. So it's G mod Z. I'll have to think about that. Wait. Okay. P to the K minus 1 is less than or equal to P to the E minus 1. That makes sense. But how is it equal to the order of the quotient group? Wait. Right. So P to the E is the order of G, and Z is a normal subgroup of G. And its order is P, right? It has order P. Okay, so then of course that makes sense. The G mod Z is going to have order P to the E minus 1. There's a P to the E over P, right? So you do that for each step of the induction. So G mod Z has a normal subgroup H star of order P to the K minus 1. Right? Okay. Now by correspondence theorem, there is a subgroup H of G containing Z and containing Z with H star being H mod Z. Moreover, H star is normal subgroup of G mod Z. That implies H is a normal subgroup of G. Give me a second. Okay. So, hello? Okay, so I believe that this makes sense. I mean, correspondence theorem allows you to have the bijective correspondence between the subgroups and the subgroups that contain Z. I mean, here Z is a normal subgroup. Okay, yeah. So H star is equal to H mod Z. That also, because H star has order P to the K minus 1, right? And okay. But wait. H is equal to H mod Z. And H mod Z is going to be normal subgroup of G mod Z, right? Okay. And that implies H is okay. H mod Z is a normal subgroup of G mod Z. That implies H is a normal subgroup of G for sure. But we know that this has order P to the K minus 1 because of the definition here. So that implies the order of H must be P to the K as we need. Okay. It's kind of straightforward enough, just you need to um, you know, detail a few things out. Okay, so a simple group is a group, a non-trivial group that has no normal subgroups other than the identity and the group itself. Okay. So proposition 2.107, which says that if you have an abelian group, then it will be simple if and only if it is first of all finite and it has a prime order, right? This makes sense because for the simple condition you need the abolishment of all normal subgroups, right? So let's see. So if G is finite of prime order P, then G has no subgroups H other than uh, the identity and the group itself, because there will be no other subgroups. I mean, by Lagrange theorem, you're not going to have any divisor of P. So yeah, that makes sense. That it's going to be simple. So that's the forward direction. The other direction is that when you have prime order and it's finite, it must mean that it's abelian. So this is cool. If you have a group of prime order and it's finite, you can just have commutativity. Yeah, you have commutativity and you have simple. Okay, so that's cool, right? Yeah, so assume that G is simple. Since G is abelian. Wait. Is this a forward or the backward direction? This is the backward direction. Okay, right. This was, wait. Okay, so this is the forward direction. That was the backward direction. Yeah, we proved that if we assume that G is finite and has order P prime, then it implies it is abelian and it has I mean it is a simple um, abelian group. Okay, wow. Yeah, for this one we have to assume that it is simple. Um, as it is abelian, every subgroup is going to be normal, and since and so G has no subgroups other than 1 and G itself. Right? So if you take a non-trivial element um, from the group and you generate a cyclic subgroup from there, then the cyclic subgroup has to be equal to the whole group itself. Right? Now, if X is like a cyclic subgroup which is non-finite, so it's infinite, then all the powers of X are going to be distinct, right? So your powers are not going to repeat. Um, mm-hmm. And so the cyclic subgroup generated by X square would be a subset of the cyclic subgroup generated by X. Okay, so that um, is this forbidden subgroup of X, because you need all the powers to be distinct, right? So that's a contradiction. So for every element in X, um, you have the finite order. The only cases where it will not have finite was the cyclic case that we saw that's contradictory. So if X has finite order M and M is composite, right? So you can write it as a product of two numbers K and L. Then the cyclic group generated by X to the K is a proper non-trivial subgroup of the cyclic group generated from X, which is also a contradiction because mm-hmm, okay, because you need all the powers. Okay, you need wait. Mm-hmm. Right, because you have only two subgroups, 1 and G, so this cannot be a subgroup of X, which is essentially the group itself, without being the group itself or the identity. There's no other option. So G is equal to the cyclic subgroup generated by X, and that is just the prime. Right? It is of prime order. Okay. Okay, so that got messed up for a while, but I think the general idea is simple enough. Okay. It talks about the alternating group for a while and some stuff related to that. I'm not sure if we do need it, but I guess we do. Okay, let's see if we can do some of this. So, A5 alternating group of 5 elements is a non-abelian and simple. Okay, makes sense. So if you you take an element that has like k conjugates, so its conjugacy class has k elements, you know, and then you take a subgroup of the group, so you take a H, you'll have to, if you wonder how many conjugates does X have in the subgroup, right? So that will be the conjugacy class with respect to the subgroup. So this is X to the H, right? So you'll be considering all the conjugates of X with respect to H. And this is going to be a subset of the conjugacy class of X itself. Yeah, A5. I've also known that it comes up for Galois theory, quite a number of times, but I don't know if about much about that either. So yeah. So this lemma says that all three cycles are conjugate in A5, right? So right. Okay, so you take G to be S5, and alpha is a 3-cycle 1, 2, 3, and H is the alternating group A5. Now we know that alpha, the conjugacy class of alpha is 20. So what that means is that there are 23 cycles. So there are 20 cycles of 3 characteristics in S5. Okay? And they take that as a given, but that's easy to check because they did that in some exercise. So that's the conjugacy class for this 3-cycle. Now, therefore, 20 must be equal to, remember this, right? So this was just again the counting formula, but the order of the conjugacy class is equal to the order of the group over the order of the centralizer of that element. So here the group is S5 and the element is alpha, so 20 is equal to S5 over C of alpha, and that is S5 is 5 factorial, that's 120. So 120 over the order of the centralizer, right? The order of the centralizer, you need all the elements that commute with alpha, right? Sorry, it's centralizer. The centralizer for this. So there will be 6 permutations in the group, symmetric group of 5 that commute with alpha, right? And these are the permutations. It's not hard to see why. Okay, so you'll have 1, 2, 3, 1, 3, 2. Then you'll have the transposition 4, 5, and then the multiplication of the transposition would be with these two, right? So you need 2 3 cycles and 1 transposition, and you have the product to get these. So this is okay. 1 2 3 1 3 2 4 5 4 5 1 2 3 4 5 1 3 2. Right? Okay. And the last 3 of these odd permutations. Yeah, last 3 of these are odd permutations. Yep. So the centralizer with respect to the alternating group, because the alternating group contains only the Wait. Okay, yeah, it's going to contain 3 elements. So the conjugacy class with respect to the alternating group is going to be A5 over CA5 alpha. And that is just, this is 60 because this is 5 factorial over 2, 60 times over 3, that is 20. So now those are all the 3 cycles that conjugate um, with respect to alpha in A form, right? And this is, I mean, these are all the cons, all the 2 cycles there, because we saw that the conjugacy class of alpha in S5 was 20 as well, so this is just the same. Okay, this is a lemma. This is a lemma to show that it's a simple group. We're not going to go through this. It's pretty straightforward to check. It's just using this lemma and the previous one. But after that, we have to check A6 is a simple group, which can be quite an exercise. Now for general cases, AN is a simple group for all n greater than or equal to 5. That would be interesting. And then we have a few theorems. Okay, well, yeah, that's so let's see what other things we can do with the alternating group. So if your n is greater than or equal to 3, every element in AN is a 3 cycle or a product of 3 cycles. Yeah, that's helpful. So if you take a permutation in AN, then alpha is a product of an even number of transpositions, right? So you have alpha is equal to tau 1, tau 2, up until tau 2q for some even number of transpositions, right? Right? If uh, right. So if we just consider 2 transpositions that are not disjoint, so you have tau, which is ij, tau prime is ik, tau prime, the multiplication, the product is going to give you ikj, right? That's a 3 cycle. But if they are disjoint, that is, they have nothing in common, so you'll have ij times kl, then you're going to have ij times jk times jk times kl, and that is equal to ijk times jkl, because you can use from here, you can pair these to get ijk and jkl respectively. So that shows that if you have n greater than or equal to 3, your every element in AN is either a 3 cycle or can be written as a product of 3 cycles. A5 is a simple group, so we'll take that for granted as of now, but you can check the proof later. A6 is a simple group. They use the second isomorphism theorem, but let's see the general case. If we cannot make sense of this, maybe we'll go and check this one. So AN is a simple group for all n greater than or equal to 5. You take a non-trivial normal subgroup of AN, right? So we have to show that the subgroup, normal subgroup, has to equal to the alternating group itself. That is, that has no normal subgroups. If you can just show that H contains three cycle. Oh, so this is interesting. He leaves half of the thing for the reader. Page 113, he has an exercise 2.91, which is that for all n greater than or equal to 5, prove that all three cycles are conjugate in A. So he takes conjugacy for granted as of now. It's not, I believe, it will not be that hard to see that, okay. So if you can just show that, like H contains a three cycle, then, by definition of, by the fact that we proved, like for n greater than or equal to 3, it must always be three cycle or product of those three cycles. So, if you prove that it contains a three cycle, then it has to be the entire group, entire alternating group itself. So, you take beta in H, then there is some I that beta moves, right? So that's a transposition. So beta of I is equal to J, that is distinct from I. Then chooses three cycle alpha that fixes I and that moves J. Right? Now alpha and beta do not commute because beta alpha of I is equal to beta of I, that is equal to J. But alpha beta of I is equal to alpha of J, that is not equal to J. Right? Because alpha fixes I and moves J. Now it follows that if you have some gamma, which is another element of H, but it is written as in this interesting way. So it's the conjugate of beta with respect to alpha. So we have alpha, beta, alpha inverse times beta inverse. So it's a non-trivial element of H. Now beta alpha inverse beta inverse is a three cycle, right? Because of 2.9. This one. Right. 2.9, which theorem is it referring to? That will be quite. Okay. So gamma is a product of three cycles, three cycles. Because alpha is a three cycle itself. Hence gamma moves at most 6 symbols. Right? So it commutes 6 symbols. You take that to be I1 till I6. Now you define a set which contains these permutations from AN that fixes all the symbols that gamma moves. Right? Now F is going to be isomorphic to the alternating group of 6 elements because of the previous lemma, because it's a simple group and the F that he considers here is pretty much similar. Right? So what that means is that gamma is now in H intersection F, because H is just a non-trivial subgroup of AN, and F is A6 itself, which is also a subgroup of AN. And Y contains just 3 cycles. So yeah. Now hence H intersection F is also a non-trivial normal subgroup of F. Okay, because A6 is simple, right? But yeah, then F is simple as well. So H intersection F has to be F, right? Because you um, cannot have H intersection F, H being anything else other than the identity and F itself, because F is simple. Right? So F then is going to be a subgroup of H. Therefore, H contains 3 cycles, and then from the conjugation it proves that it is complete. I would really say try to prove this theorem yourself. Try to prove that exercise yourself, the conjugation, and then try this. Yeah, it can be a good exercise. Same for A6, I guess. A6 directly kind of follows from A5. This general one is kind of tricky. Okay, so let's see a few more things, then we'll be done. Yep. Essentially, I mean, some of the exercises are kind of straightforward. I mean, they should be theorems themselves or lemmas that he should prove. But yeah, he goes back to exercises quite a lot. So this is the Burnside's lemma. Okay. Now D acts on a finite set. N is the number of orbits. Then the number of orbits is equal to 1 over the order of G times the summation of this fix of tau. So this tau is like all the wait, okay. So fix of tau is the number of x in x. The number of elements of the set that are fixed by tau. Okay, that makes sense. So this is the Burnside's lemma. So you can essentially get the number of orbits by the order of the group and how many things tau fixes. Okay, the proof kind of looks lengthy, but let's see. You take an element x1 in the set. All the elements are x1 till x are in the orbit O of x1. Okay. Um, Then you choose an x r plus 1, which is not in the orbit. Then you list the elements r plus 1 till r plus 1, r plus 2 till I don't know where, in the order of x r plus 1. Right? Okay, so you continue this procedure. Okay, so you can think of it like this. You take an element, you have an orbit around it, of it, and you contain these elements up to r. Then you choose the next, which will be r plus 1, which is not going to be the orbit, and you create another orbit for that, and then continue from there, r plus 1, r plus 2 until the end. And so these tau 1 till tau n of the group um, so you have Fij. So Fij is this function which gives you 1 if the tau I, so tau I fixes xj, 0 if tau I moves xj. Okay, this is a bit confusing. I don't know what's happening, but essentially you have these columns of x1 up until x1, x2, and x r plus 1, just like this, r plus 2 until a dot, a dot. Then you have tau 1, tau 2 until tau n, the elements of the group. Now x1, t1. Hmm. Wait. So F11, F21, Fi1 to Fn1. So these are all the things that fix hmm these are all the ah okay, right. So for x1, um you have all these taus that fix x1, right? So as they fix x1, so this will be um f11 and f21, fi1 till fn1, right? And so mhm. So for this particular x1, you're going to have either tau. Each of these tau would either fix this x1 or would move it, right? So from there, so this is just like for notation, I believe. Fij just means that for particular index of x, you're going to see if tau fixes it or not. So f11, f21, fi1, and you go on until n. And you do that here as well. Um, okay. Now the fix of tau I is going to be for a particular tau, how many ones you're going to have from these f's. So this f is going to either give you 1 or 0. So you count how many the number of 1 you get, and you add them for all the taus, and that is going to give you this part of the lemma. I hate this thing, to be honest. This is just, I don't know, counting stuff in a damn manner. Um, um, so that's that. Um, mhm. So now the number of ones in the first column. Okay, so the number of ones in the first column is it's going to be the order of the stabilizer, right? It's going to stabilize x1, right? Same for x2. So these columns are all the stabilizers of um the x's that you have, right? And then okay, we have the formula for the stabilizer. So essentially, for whatever that formula was, I don't even remember. For the orbit, you can write it in terms of the stabilizer and other things. So then they apply that, and this is exactly what you're going to get, right? So yeah, the result is more interesting. um, so the number of orbits can be written in this manner, but I guess I believe the idea is clear now. So he tries to use this lemma to solve some problems. So how many stripped flags are there having 6 stripes equal width, each of which can be colored red, white, or blue? So this sounds a lot like um, combinatorics, but I believe there's nothing in it that's as important um, than being kind of mostly computational. Um, the other lemmas that he talks about, this related to this color, I'm not sure what he's doing. Yeah. Hmm. But I guess we can leave it at that. can't we? I mean, we've pretty much covered all the important things that we needed to for group action and stuff. Wait. Comes with this Burnside lemma for algebras? These flag examples? That's kind of weird. We do not, well, we're going to use algebra from Rotman. That is multilinear algebra. So, I'm not sure if he uses stuff like this in exterior algebra and other things. If he does.
I don't think so. I'm trying to find out where I saw it. It was way back in chapter 8, which wasn't. It wasn't this stuff on multilinear algebra.
Yeah, chapter 8 is just algebras, okay. Okay, so that was that theorem of Burnside and Venus that he has a whole section on, okay.
On page 620, there's another version of Burnside's lemma, which looks very much like this one. But I don't see anything corresponding to that over in Hungerford. And I don't know whether we're looking at chapter 8 in this book.
I believe, like, just like in the case of group actions, he considers it for a very specific thing, not really for algebras in general. Maybe he does. I don't know.
Okay, I see we're using chapter 9 from Rotman.
Yep.
So who knows how much stuff from chapter 8 he's going to refer to.
We don't.
So if necessary, we'll look back in.
Yeah. I mean,
chapter 8, I suppose.
This is just a section of that. Wait. Which 1.5 is characters where he has his Burnside theorem. This flag stuff seems kind of arbitrary to me.
It just seems like a fun application, so
Yeah.
I didn't actually read it.
Okay, yeah. Maybe others are interested, maybe they can look, but neither am I. So that makes sense. We're not going to have much problems in the PSET from there too, so that's fine. So yeah, we're done with the group actions, and we're ready to go to the, what was that? The second chapter on groups, or finite abelian groups and stuff there. We've got a lot to tackle next lecture. Yeah. So then we'll later go into silo theorems. I believe we're going to spend a whole lecture just on silo theorems. But yeah, before that we'll have to do some theorems for the finite abelian groups, which we didn't during our first time encountering group theory. So that's that. Okay, so tomorrow we have the PSAT discussion for PSAT 5. A lot of interesting problems to talk about. So yeah.
All right, good session. Thanks a lot.
We'll
see you tomorrow. See everybody tomorrow. Ciao.
Okay, see ya tomorrow, and yeah, good luck.